Hello everyone. I'm going to continue talking about some of the basic trig identities that we have. The next ones I want to take a look at are called the cofunction identities. So here I have a right triangle, side lengths labeled x, y, and then r. If we think about this in the coordinate plane, r would be your radius, then you have your x and your y values. Those are basically your sine and your cosine. And then my two angles here I labeled as alpha and beta. So first, let's just think about the sine of alpha. So we know that the sine is equal to the opposite side divided by the hypotenuse. So opposite to alpha is y, and then the hypotenuse is r. So the sine is equal to y over r. Let's do the cosine of alpha. Cosine is the adjacent side divided by the hypotenuse. So adjacent is x, and then the hypotenuse is r. Now let's switch to our other angle, and let's do the same thing. When we switch to the other angle, our opposite side and our adjacent side also switch. So the sine of beta, opposite to beta is x, and then the hypotenuse is still r, and then the cosine of beta is equal to y over r. And then hopefully you can see here that some of these fractions are equal to each other. So the sine of alpha is the same as the cosine of beta, and the sine of beta is the same as the cosine of alpha, which makes sense because when we switch angles, those opposite and those adjacent sides also switch. So we have the sine of alpha is equal to the cosine of beta, or we also have the sine of beta is equal to the cosine of alpha. But we also know that alpha and beta are directly related to each other. So they're the two acute angles in a right triangle. So we know that the angles in a triangle have to add up to 180 degrees. We already know this is 90. So that means alpha and beta have to also add up to 90, which means that they're complementary angles. And that's where this idea of cofunction comes from. So cofunction, that prefix co, basically we're looking at the fact that they are complementary angles to each other. So I know that beta is equal to 90 minus whatever alpha is, or vice versa, alpha is 90 minus whatever beta is. So I can take these two equations and I can rewrite these a little bit. So the sine of alpha is equal to the cosine. Now instead of beta, I can write this in terms of alpha. So this is 90 minus alpha. Or we could write this the other way as well. So I could say the cosine of alpha is equal to the sine, so the cosine of alpha, now instead of beta, 90 minus alpha. So what this means is that the sine of an angle and then the cosine of its complement, those are the same. So for example, the sine of 40, that is going to be the same as the cosine of the complement, which is 50, or vice versa. Now, this idea can be extended beyond just a right triangle as well. And if we look at it within kind of our coordinate plane, considering the unit circle, we can get similar ideas for all of our trig functions. So let's just write out our general ones. So the sine of theta, that is equal to the cosine of the complement. And I'm going to write this using radians. So instead of 90, let's do pi over 2 minus theta. Or vice versa, we could do the cosine of theta is equal to the sine of pi over 2 minus theta. Then we have the tangent. This is a cofunction with cotangent. So the cotangent of pi over 2 minus theta, and vice versa. The cotangent of theta is equal to the tangent of pi over 2 minus theta. And then the last pair, the secant and cosecant. So the secant of theta is a cofunction with cosecant, and vice versa, we have cosecant of theta and secant of pi minus theta, pi over 2 minus theta. So there are the 6 cofunction identities. Now hopefully the names of these different trig functions make sense. Sine, cosine, right? So the sine and the cosine are cofunctions. Tangent and cotangent. Secant and cosecant. So each of these has that prefix co, which indicates that it is a cofunction with the other one. Okay. Now the last identities I want to take a look at are the odd and the even identities. This is something we know from graphing these different functions, but odd and even basically describes what sort of symmetry they have. The other way we can look at it is on the unit circle as well. So let's just pick out some random angle. So let's say up to here. And let's say that this is angle theta. And this point is x, y. Now what if I do the opposite angle to theta? So if I rotate down this way, and I do negative theta, we know we have this symmetry over the x-axis. The x value stays the same, but now we have a negative y value. So we know that cosine basically represents the x value, sine basically represents the y value. So now using this idea, we can write some identities for odd and even. So the sine of negative theta, so the sine of theta would give me y, but if I do the sine of negative theta, I get negative y. So this is the same as the opposite of the sine of theta. So just a little shortcut. So if I have the opposite of an angle, this is odd, so I can bring that negative outside. If I compare that to cosine, the cosine of negative theta, the cosine of theta gives me x, the cosine of negative theta also gives me x, so this one just stays the same. So that negative goes away. So this is an even function. Now if we extend that idea to the other ones, so the tangent of negative theta, tangent of theta would be y over x, tangent of negative theta would be negative y over x, so it's the opposite. So the negative tangent. And then our reciprocals that go with this, called as cosecant. Cosecant is the reciprocal of sine, so this is also odd. The secant, this is the reciprocal of the cosine, so this one is also even. I wrote that bad. And then the cotangent, the reciprocal tangent, so this one is also odd. Okay. So sine, odd, so it's the opposite. Cosine is even, so it stays just the same. Okay. Now let's finish up by taking a look at one example here. So this example, I'm going to be using our cofunction identities and our even-odd identities. So I'm given a value for the tangent of theta, it's 1.28, and I want to find the value of the cotangent of theta minus pi over 2. So what I'm going to do is just some rearranging here, and maybe a little bit of substitution at the end, so I can figure out what this value is. So the first thing, if I look at what's inside my parentheses, this is kind of backwards to what we have for our cofunction identities. So normally we do pi over 2 minus theta, but I can write it like that. So first I'm going to factor out a negative sign, factor out a -1. So if we do that, factor out the negative, we end up with negative theta, and then plus pi over 2. So the signs of those just switch. We can clean that up a little bit. So the cotangent, this is going to be the opposite of pi over 2 minus theta. So just switching those around. Okay? Now we have the cotangent of something opposite. We know that cotangent is odd, so this is going to be the same as if the negative was on the outside. Okay, so the opposite of the cotangent of pi over 2 minus theta. Cotangent of pi over 2 minus theta, this is our cofunction, so we end up with the opposite, and now we can replace this with the tangent of theta, because these two are the same. So cotangent of pi over 2 minus theta is the same as the tangent of theta because they're cofunctions. So now we have the opposite of tangent of theta, but we know what the tangent of theta is equal to from up here. So then substituting that in, we get negative 1.28. And there's our answer. So that wraps it up for our basic identities. We have our cofunction ones, and then we have the even and odd ones, and together with the reciprocal and quotient ones that we talked about earlier, that covers all of the basic identities for trig.